Probability describes the likelihood of a certain event occurring. So here we see the probability of A, and oops, this should have still been around A. The probability of A occurring and the probability of A not occurring is equal to 1. So the probability of A not occurring would have been the area out here, but it got messed up. So here we have two events, A and B, and again, the total probability is 1. The probability of A and B happening is denoted this way, probability of A and B. And if these two events are independent, if A and B are independent, then this probability is just the product of the two. For example, say we were assembling computers and we bought the PC from one vendor and the monitor from another vendor, and the PC had a likelihood of failing of 10%, so the probability of a defective PC was 10%, and the probability of a defective monitor, so that would be B, probability that a monitor would be defective would be 5%. Well, then the probability that our assembly, our PC and monitor assembly is defective is the probability of a defective PC times the probability of a defective monitor. So that would be 0.005, or 0.5%. And here we have the probability of A or B. You can see the probability of either one of these occurring. And this is equal to the sum of probability of A and probability of B minus the probability of both A and B happening. And if the two are mutually exclusive, then that term is 0. So if A happens means B cannot happen, then this term will be 0. Now we often want to use our sample data to predict population behavior. And typically the behavior is not identical. So typically our sample is not going to behave exactly like the population, meaning it won't have the same central tendency, it won't have the same dispersion. In a lot of situations, the population behavior follows a known mathematical function to a given degree. And what we use our sample data for is to compute the parameters of those functions. For discrete variables that can only have certain values, then these functions are probability mass functions. And for continuous variables, they're called probability density functions. Here's an example of a probability density function where we have somebody throwing a horseshoe at the target, which is xm away. And if we sampled their throws, then we would want to come up with this function here representing the probability density function. So the probability that their throw is a certain distance away. And there are different functions, and which function applies to a given situation is often known from experience. There's also a goodness of fit test that can assess the suitability of a probability function to a certain situation. We'll look at the goodness of fit tests later. Probability mass functions. Again, this is the probability function for a discrete variable. And it's given by this notation, probability that event xi will occur, or that we will have a value xi. The average value, or the expected value for this population, is called the mean. And since the sum of all the probabilities is 1, then the mean is given by this sum here. It's the weighted average of all the values. So the sum of all the values multiplied by the probability for each value. And the population variance is the dispersion for the population, and it's given by this equation. Binomial distribution is one important probability mass function, and in this case our variable can have either only two values. It could either be success or failure, and the probability of a success is called p, and that's a constant. And we have to assume that each of our trials are independent. So if we have one success with one trial, then that doesn't affect the probability of having a success with the following trial. The probability of a given number of successes, n, little n here, is given by this equation, where we have big N is the number of trials and P is the probability of a success. So we could also look at the probability of no successes, which is just if they're all independent, that's the probability, well, 1 minus P here and here is the probability of a failure. So here we have the probability of failure to the raised to the power equal to the number of trials. So this is just the probability of them all being failures. And here's the probability of every trial being a success. Again, it's just the probability of a success raised to the power of the number of trials. There are cases where we know the average number of successes over an interval, and we want to find the probability of some number of successes. Say we know that over a 5-minute span, the average number of customers is 5 or 3. Then we could use the Poisson distribution to say what's the probability of having 8 customers over a 5-minute span. Whenever we have n trials, the average number is given by the product of n and the probability. And if we have a big number of trials, as n goes to infinity and p goes to 0, then this is still going to be some finite constant representing the average number of successes over the interval of n. So the Poisson distribution is given here. It says the probability of having n successes. And a is the average number of successes, and e to the negative a divided by n factorial. Here are Poisson distributions for intervals of 20 and different values of mean number of occurrences. Again, that's a. We have to assume that for a given value of a, if we have 2 different intervals, then the probabilities of occurrence are the same for those intervals. And also that the probability of occurrence is independent of other occurrences, which we stated already with the binomial distribution, to which the Poisson distribution is related. So here we have a case in blue where for 20 trials, there's an average of 1 success. The blue curve gives us the probability of having different numbers of success over 20 trials. So here's the probability of 0 successes over 20 trials, 1 success, probability of 2 successes, 3 successes over 20 trials. So you can see what the Poisson distribution does. And here, for a different system, if we had the average number of successes was 4 for 20 trials, then this curve would give us the probability of different numbers of successes for 20 trials. So here we could say the probability of having 7 successes is about 0.1 out of 7 out of 20 trials. 7 successes out of 20 trials would be about 0.1 if A is 4. And you can see the different curves for the different average number of successes. Oftentimes, we might want to know the probability of no more than k events occurring, or no more than k successes occurring for a given number of trials or over a given interval. And that's the probability that n is less than or equal to k. To do that, we just add up the probabilities of the different values of n from 0 up to k. So if a is 1 and we wanted to know the probability that we would have 2 or fewer successes, then we would just add up these probabilities. So here it's 0.37 plus 0.37 plus 0.19, and that would give us the probability of having 3 or fewer successes. So these probabilities are important in determining different parameters in engineering applications, such as estimating the number of defects in a certain batch.